All right, so we're going to move on again. We're staying in the topic of human sensory psychology and sensory abilities here, but we're going to move on to now the sense of hearing. But as we move into hearing, we also need to talk about sound as well. And just like we did with vision, we talked a little bit about light as the stimulus for vision and the nature of the range of light energy that we can detect, the visible spectrum of light. And we also want to say a few things similar about sound in terms of the ways that we can characterize and describe sound waves and the range of sound waves that the human ear can detect. But in addition to that, there's a few other physical characteristics of sound that we want to talk about here. And that's also part of the field known as acoustics, which relates to the way sounds work in the environment and how that affects our ability to detect sound. So let's start, of course, just with the simple physics of sound. So sound producing events are essentially vibrations. And what happens is that when there's a vibration, like maybe just clapping my hand, or as you see in the picture here, the tuning fork, and what happens when you strike the tuning fork is that the forks begin to vibrate back and forth like this, right? And just like when I clap my hand, right, there's compression of the air between my hands. And there's likewise between the tuning forks, there is compression of the air molecules between the forks as they press together. And then as the forks move apart, that creates the opposite of compression known as rarefication of the air. And so that compression is essentially, we can measure the pressure in the air, right, with a barometer, I guess, right? And so we could measure that as a high pressure wave front that would be then traveling through the air. So once we compress the air at this point here, when I clap or when we strike the tuning fork, there is a wave front, a high pressure wave that will then start to expand from that point in all directions. So heading out more, basically in a circle or spheres, I mean, really. And so this spherical wave front heads out in all directions. And given the fact that in a tuning fork, you're going to strike the tuning fork and that's going to cause continuous vibration that will last for several seconds. It's not just a single wave front, but it's going to be multiple wave fronts happening over and over again. And the exact rate at which these wave fronts are emitted corresponds to the exact rate of the vibration of those tuning forks. So as the forks vibrate back and forth at certain speeds, that's going to cause the pressure wave to now be emitted from this point at the exact same rate. So what is that rate? Well, let's imagine, for example, that we had a tuning fork that, because of the nature of the thickness and length of the tongs, or tines, I should say, vibrated at 500 hertz. That means 500 times per second, and hertz is the unit for frequencies per second, like that. Well, that's going to cause the wave front to then vibrate 500 times per second. And that means there's a traveling wave that's repeating itself through the air 500 cycles per second or 500 times per second. And you can kind of see that in the image here, right? These waves that are sort of moving away from the tongue on the right-hand side there. And if that's a 500 hertz tuning fork, that means the wave is going to have a frequency of 500 hertz. So let's understand something about these pressure waves and the frequencies. So we can graph this wave. And one of the ways that we can do it is that by graphing the intensity of the wave, such as the actual air pressure level at the high point where you have the compressed air and you have higher pressure, that's going to raise on this graph here, the air pressure is on the y-axis. So we're going to see that line go up, right? And then behind it is the rarefied air, the air that's less compressed. And so it has low pressure. And we'll see that curve drop down. And that's going to give us these peaks and valleys in the curve, right? The higher peak is the compressed air. The valley is the rarefied air. And so in between will be continuous variation in the pressure between the peaks and valleys. And you're going to get this nice up and down curvy graph that essentially is a sine wave function. And on top of that, another way to think about this wave is the pressure wave traveling through the air is pretty equivalent, if this helps you conceptualize the concept, to a wave traveling across the surface of water. So if you were to imagine a pool and you were to drop a small stone into the center of the pool, what's going to happen is that stone presses down on the surface of the water, right? And that compresses the water and makes a high pressure wave that will then travel out, in this case, a circle, because the water just has a flat two-dimensional surface, right? So it's going to travel in a circular pattern away from the point where you drop the stone. And if you could put your eye right at the surface of the water, you would see this wave go up, and then behind it would be a dip, because there would be, behind the high pressure wave would be a low, right, where there's low water pressure. And if you were to continuously drop stones into the water 500 times per second, if you could do such a thing, then you would see this kind of continuous 500 hertz wave pattern flowing across the surface of the water. But now in this case, with a sound such as a 500 hertz vibration from the tuning fork, you're just going to have these pressure waves traveling through the air, and you can't see them. But imagine if you were to put up a marker somewhere in the room next to where the tuning fork is, and you could see those waves, then you would be able to count 500 peaks per second or 500 valleys per second, however you want to do it, passing this marker in the space every second, 500 peaks and valleys, right? And so those peaks and valleys, we can break those up. And so if you see here on the top, what's been highlighted here is one complete repetition of this wave, right? So since this wave is repeating itself with peaks and valleys, we could pick any point there and cut it. And so in this point, they have cut it basically where it repeats itself at approximately every 1.5 seconds, right? So this would have a fairly slow rate of essentially, 1.5 cycles per second. So 1.5 hertz, right? Or no, that's not right. It's in 1 second, it only goes less than a cycle, right? So it would really be probably something around 0.75 hertz is what that would be, right? About 3/4 of a cycle occurs within that first second. We have to go all the way up to, excuse me, 1.5 seconds before we are getting close to repeating the full cycle. And so by copying and pasting that out down there in the middle, we see the repetition there with the peak in the center and the valleys on either side where we've pulled that one cycle out. And so we can see how that corresponds again to the rarefication, pressure rarefication, that repetition that's occurring as the tuning forks will vibrate. So we can define then a couple of different things, right? So we can define, as I had previously noted, the frequency of the wave, and that's how many cycles repeat in a given amount of time. So in this case, that looks to be about 0.75 cycles per second, or 0.75 hertz. And we also can describe the amplitude of the wave, and the amplitude corresponds to the actual pressure changes, right? So that dashed line in the center that goes horizontally across out from the y-axis is essentially the zero, right? And so you see the pluses and minuses on the y-axis suggesting that there would be a sort of zero neutral air pressure level, and the compression makes it go positive above that line, and then the rarefication makes it go negative. And so we could imagine a difference between a very light tap with the tuning fork that would create the same frequencies of vibration, because that's determined simply by the thickness and length of the tines on the fork. But it would change the degree of compression, right? So if you just lightly tap it, you're just going to get a little bit of movement of those vibrating tines. And so it's going to have low air pressure, and it's going to have a low amplitude of vibration. But if you really whack this thing hard, then it's going to be, clapping back and forth at a high intensity, and that's going to create higher air pressure, right? So we can see these characteristics on this graph. And so we can see the amplitude of the wave is defined as its height above that central zero line, essentially, right? And it should be symmetrical so that the height of the peaks are equal to the height of the valleys, right? Now here I've defined the timing part of it as the period, which is the literal time between peaks, or the time between any sort of repeating part of the cycle. So if I come back here to this previous graph, the period, which is the amount of time it takes for that cycle to repeat itself, is 1.5 seconds, right? So that's exactly what that is, right? But we can also calculate the inverse of the period. So if the period is defined as what is the time per cycle, which in the previous case was 1.5 times per cycle, 1.5 seconds per cycle, we can invert that and say how many cycles in a given amount of time. And that's what we call frequency. And so in the example that I gave before, if you were able to see those peaks passing through some marker in space, you would be able to count for, let's say 500 hertz, you would count 500 peaks per second in that case, passing your marker. And that would be the frequency. Basically, how frequent are these, is this cycle repeating itself? So we can now imagine that we can describe this simple vibrating wave, this sine wave, we can call it, in terms of its period or frequency, which is a kind of a measure of how fast the cycle repeats itself, and also its amplitude, which is how much air pressure has been created here. And we're going to say that when it comes to sound, such a sine wave creates what's known as a pure tone. And that pure tone is just basically the idea of having a pure frequency. Now, I don't have it incorporated into the PowerPoints, but one thing you can do to get an idea of different pure tones is there are plenty of places on YouTube where you can do this. So if you just go into the YouTube search box and type 500 hertz tone, you will see a few different channels that will just play a 500 hertz tone for you. And you can hear what that pure tone sounds like at 500 hertz. You can also then change the value. You can go search up a 600 hertz tone or a 1000 hertz tone, and you will also be able to hear the differences. But what you will notice is that the nature of a pure tone is very unusual, right? It doesn't sound like anything that we naturally encounter in the real world. It's just like a single note, just obviously I'm not going to replicate a pure tone by singing it, but it will just be a pure beep, right? And that's not a pure tone because the human voice doesn't create pure tones. That is just a single frequency. Rather, this is why I'm talking about this, is that the sounds that we hear in our natural environment, which includes the human voice, as well as musical instruments or hands clapping or machinery or whatever sounds that we might hear, are all complex tones. And a complex tone can be sort of conceived of as really the sum of many different pure tones that have now all been added together and combined together. And so what we want to understand here is when we add together different pure tones, we can essentially sum them together, and that will create a new complex tone from that. This process is known as Fourier synthesis, right? So I have an example at the bottom, very kind of crudely drawn, I guess, but what we can see there is possibly three on the bottom left, three different pure tones. And the one on the top would be a high frequency tone because the peaks are repeating themselves much more often than the one in the middle, which is kind of a medium frequency. And then we have a lower frequency where we only have just, 1.5 of a waveform there in that little window of time. And if we add them together, what we might get is something like we see on the bottom right, which is a much more complex looking waveform that has elements of the low frequency components, but it also has elements of the high frequency components embedded within it. And so you're going to end up with a sound that doesn't sound like a pure tone. It's going to sound a little like something else. Now, the way in which these different sine waves, pure tones add together also depends on their phase relationship, which is what I have in the middle of the picture here as well. So when the two frequencies are perfectly in phase with each other, so that is maybe two peaks are hitting at the same time, those two peaks are going to have high pressures, and that's going to create a high sum, right? They're going to have two positive values of air pressure that occur at the same time, and they're going to add together to create a much larger number. And likewise, when two valleys occur at the same time, they're going to essentially sum their values together to create a very low valley. But on the other hand, sometimes two different tones might be out of phase with each other, which is what we see here when the peak perfectly coincides with the valley. And then you end up sort of canceling things out, right? And so in that case, you end up maybe with the resultant sum of those two tones essentially cancels each other out and creates almost a very weak sound, perhaps, which is kind of an ironic thing to think about, right? Hard to imagine two tones canceling each other out. But the idea is that based on these different phase relationships between the sound can actually create, you can get this kind of an effect that creates like a warbling effect with the sound or some other sort of unusual effect. In fact, if you're a musician, you might know that if you play guitar, you can have a phase pedal, right? And what a phase pedal does is usually it will split the signal coming from your guitar into two separate signals, and then it will phase shift those signals so that now between those two signals, one of them has been shifted in time relative to the other, and that creates a phase shift effect that will create a specific kind of sound effect that you might be searching for. Flanging effect does a similar kind of a thing as well. So, and of course, we can reverse this process. So Fourier synthesis means the adding together of pure tones to create a complex tone. And Fourier analysis is when we can take a complex tone and then try to determine what are the simple tones that make up this complex tone. And so this is also then sometimes referred to as spectral analysis, because what we want to do is that when we are maybe we were trying to understand the nature of the noise in a given environment. If we're listening to a noisy environment where there's maybe lots of machinery, it's a factory environment, or maybe it's a crowded place like an airport, and so there's lots of people talking and footsteps and other kinds of sounds that people make. This is going to be a noisy environment, and that means it's going to be a very complex noise that's made. And by a complex noise, we mean that there's lots of different frequency components that are present. And by performing spectral analysis or Fourier analysis on that noise, we can determine what frequencies are present in that noise and in what relative proportions, right? And so this is what I have, on the top right, we see just the basic spectral analysis where we've broken that complex waveform down into its component frequencies. But on the bottom left, we have a different kind of analysis. It shows the same three frequencies, but what I've done is I've taken the three frequencies and put them on the x-axis and made essentially a bar chart that shows that the height of the bar corresponds to the relative amplitude of each of the three frequencies. So not only do we know that we have three different frequencies present, but we know that the power or amplitude of frequency 1 is stronger than the amplitude of frequency 2, which is stronger than frequency 3. We can capture that also in what's known as a spectrogram. So in the bottom right, we're going to put time back on the x-axis, but put frequency on the y-axis here, and we're going to use the thickness or heaviness of our bar graph, line graph, really, in a way, or scatter plot, maybe, to capture the amplitude. So in this case, frequency 1, which is possibly the lower frequency, has a higher amplitude because it's a thicker blob on the graph. But all of these are useful because if you want to know something about the nature of a noisy environment, doing this kind of Fourier analysis or spectral analysis of noise can tell you what frequencies are present. Now, why might this be useful? Well, we're going to talk later in the semester about designing auditory displays. But we can say a little bit about this now, which is that if you have, let's say, a warning siren that might need to be sounded in a given environment that's already noisy, one thing you want to do is ensure that the warning siren is distinct from all of the noise that you would expect to be present in this given environment. So that means obviously it needs to be sufficiently loud, but you also want to ensure that maybe it's sufficiently different than the noise. And by different, I mean a different frequency. So if you determine that the noise of this environment has a particular set of frequencies that are very prominent in it, then we might determine that our warning siren can be a completely different frequency, and that makes it a little bit easier to detect because it doesn't overlap the sounds and their frequencies that we would find in that environment. So there's some value in being able to do that. So here I have on this slide simply just definitions of our terms here, right? So we're interested in frequency defined as cycles per second. The official unit for that is hertz, abbreviated Hz. Now, amplitude, I said before that that's essentially the air pressure levels, right? And you can measure that with a barometer, for example. But part of there's a problem with this, which is that if you were to actually measure the actual pressure level of the air, the range of values that we would end up with would be a huge range of values that is really problematic to deal with. It would range from from very low pressure levels all the way to 10 to the 12th power. So we're looking at massive changes in air pressure. So we're not going to talk about pressure levels using any sort of actual SPL levels, right? SPL levels means sound pressure level, or any barometric readings or anything like that. So we're going to compress that scale using a logarithmic function, and that's the decibel scale. That's abbreviated dB with a lowercase d, uppercase b. So what we know is here is that the full range of human hearing, when talking about frequency and the hertz of the sound, ranges from 20 hertz to 20,000 hertz. So 20 hertz is a very low rumbling sound, and 20,000 hertz is a very, very high-pitched sound. Now, that's assuming a young, healthy adult. So when we're talking about older adults, for example, we're going to start to see some decline in hearing that would lower the 20,000 down to, say, 17 or 16,000, and maybe even a little bit more. And certainly with older adults, we're going to be seeing even some hearing loss that goes down into maybe more typical ranges, because we don't really hear sounds in that upper end very much in the natural environment. Human voice, for example, tends to be somewhere around 1 to 2,000 hertz. And so you're going to find sounds more like that. And of course, a lot of musical stuff is below 1,000 hertz too. So we're going to keep most of the stuff that we really want to hear is usually 5,000 and below. But you even still have some hearing decrement for people who are older, even in that range. And that's, of course, not to mention people who have hearing loss because of maybe noise-induced hearing loss, which actually usually causes what's known as a 5K notch. And because the 4 to 5,000 hertz range is actually the most sensitive part of our hearing, it makes sense that if we get exposed to loud noises, especially repeatedly, say from some occupational exposure from being in a noisy environment, that the most sensitive part of your hearing is going to be the part that's most affected, which is around 4 to 5,000 hertz. And so you'll see a notch when you look at someone's threshold graph of their hearing. And if they have noise-induced hearing loss, you're going to see kind of a drop in those thresholds because of that, or really a rise in the threshold, a drop in sensitivity, right? And that notch in the curve is typical of noise-induced hearing loss. But for the range of amplitudes that we're talking about, that the human is sensitive to, since we're going to use the decibel scale here, the logarithm involved in the decibel scale keeps this at a nice manageable range from 0 dB to about 130 dB, give or take. And that upper end is really simply just the limit of what our ears can tolerate, because beyond that, we're looking at something that could actually damage the ear, blow out your eardrum or something, in which case you will clearly not be able to hear that because you would have damaged the ear to the point that you wouldn't hear anything. So I want to talk a little bit here about how to define the decibel scale, and we can see how this works. And it's important. There's a reason I want to do this, because there's some properties and interesting properties about the decibel scale that make it useful. And I want to make sure that you understand those properties. So here's the formula for calculating dB. So it's 20 times the logarithm of a ratio of two numbers, P1 over P0. And P1 is the sound that we're trying to measure the decibel level of, right? So it could be some particular tone. 500 hertz tone, like mentioned before, tuning forks, right? So maybe I want to know the decibel level when I strike these tuning forks. So what I need to know, though, is I need to know P0. And here that means the smallest relevant amplitude that can be detected. So what does that mean, relevant? I put the asterisk on that. Well, that's defined here as the absolute threshold of that specific frequency. And that's important because I said earlier that 4 to 5,000 hertz range is the most sensitive part of our hearing. Or I've kind of exaggerated because here I also wrote 1,000 hertz. So sorry for the inconsistency there, but we're also pretty sensitive to 1,000 hertz tones too. And so in this case, the idea is that the actual pressure level of the tone that we can hear at the absolute threshold will be different for different frequencies. So if I'm presenting a person with a 500 hertz tone at P1, I'm not presenting a person, it's not just psychophysical. If I just have a particular 500 hertz tone and I want to know the decibel level of that, what I essentially want to know is how much more intense is this P1 tone relative to the intensity level of that same frequency that can just be barely detected by a human. And so the P0 is essentially a reference tone, right? And it's basically at that particular frequency, what is the absolute threshold of that frequency? And then I want to know P1 is going to essentially, in the ratio between P1 to P0 is going to essentially tell me how much louder the measured sound is relative to the intensity of the absolute threshold. And once I know that, then I can compute the rest of the equation here by taking the logarithm and multiplying by 20. So that might have been a kind of a confusing definition and explanation, but maybe the math here makes a little bit more sense, because look at the bottom here. Let's pretend that I am measuring the threshold, or sorry, I'm measuring the decibel level of a sound that is right at a person's threshold. So I have a very faint tone, 500 hertz, let's just say, or 1,000 hertz maybe, that is just barely detectable, right? A human could just barely report hearing it. And so it's right at your threshold. Well, the ratio in that case would be 1, right? The amplitude of P1, since it's equal to the relevant amplitude at that threshold, it would be equal to P0. And so the ratio P1 over P0 would be 1, right? They're essentially the same pressure levels. P1 and P1 equals P0, right? So since our ratio is 1, the logarithm of 1 is 0. And you can get a calculator out and check that. 20 times that will give us 0. And so our answer will be 0 dB, right? So that means the 0 dB is our measure of the absolute threshold. Of course, that sets the bottom of our range, right? So as I said before, let's come back to the previous slide, the range of our hearing starts at 0 dB and goes up from there, right? So we could possibly, in principle, present sounds that have negative dB, right? We would not expect to hear them. Depends on what our reference tone is, but if we set P0 at our threshold, then 0 dB means the weakest sound that we can hear. So now what happens if we double the pressure level? So let's continue our example. So with our first tone that we measure, we set it equal to P0. So what if we double P1? So now the pressure level of P1 is twice that of P0. So now we're going to have a ratio of 2, right? And that means we take the logarithm of 2, and that is 0.3. Multiply that times 20, and we get 6 as our result, 6 dB. Let's try this again. So let's double the pressure level of P1 again, so that now it is 4 times as loud as P0. And the logarithm of that is 0.6 multiplied by 20 gives us now 12 dB. So there's a pattern, right? Once we started at 0, if we double the pressure level of our stimulus, it jumps up to 6 dB. When we double it again, it will jump up now to 12 dB. And so if we continue with this, and if we doubled it again, so that now we have 8x, P1 is 8x times P0, right? And our ratio is 8. We're going to jump up to 18 dB. So every doubling of the sound pressure level results in a fixed 6 decibel increase. And so you can see exactly the scale that we're dealing with here, because every time we increase by 6 decibels, that corresponds to a doubling of the sound pressure levels. So when we go all the way up to 120 or 130 dB, we really have increased we went through many, many doublings, right, of our sound pressure level. And that is creating that huge exponential increase in the actual pressure levels. And so the logarithm helps us keep that at a manageable, nice linear scale of 0 to 130 dB is essentially the range there. But that's useful to know, right? To know that every time we double the sound intensity, the actual amplitude of the pressure levels is going to raise the decibel level by 6, right? Now, here's a couple of examples, more than a couple, I guess, so you can get a good sense of what decibels really correspond to. So if you're in a very quiet environment, you just have a light rustling of leaves, right? That's just 10 dB, just barely audible. So if you're in a normal room, like a classroom on campus, 50 decibels. Now, where's the sound coming from? Well, that's the sound of simply just things like the fans of the HVAC system blowing cold air. So as I sit in the room that I am now, I can kind of hear a low whoosh from the air conditioning that's going in my house, right? And so that whooshing of the air conditioner blowing out is going to be close to 50 dB. It might just vary a little bit depending on the nature of your system and so forth, but that's just generally what we're at here. So notice a broadcast studio is much quieter than that, at 20 dB. And that's because if you're doing something like recording somebody who's going to sing a song and you want to record their voice so that you can make music in this regard, those microphones are very sensitive, and you want to make sure that they only pick up that person who is singing and they don't pick up a lot of background whooshing. So you need to ensure that all of the background noises that would normally occur in a regular room are eliminated. That's also true, say, for something like a radio broadcast booth. So a person's in broadcasting a radio, it's a talk radio station, and people are talking into their microphones, and you don't want to broadcast over the air so that the audience who's listening hears background noise, whooshing, rumbling sounds from the AC, from cars from the outside of the broadcast building and everything like that. So you have to have good sound insulation to keep that quiet. The human voice, we're going to add into that now a little extra sound. So we're going to go up to 60 dB. If you're in a car driving, right, there's a lot of road noise coming from the wind rushing around and in and out of small cracks in the windows and the sound of the tires. And so that's 70 dB. If you're walking down a busy urban street, 80 dB. If a big heavy truck drives by, maybe that's going to be 90 dB. And if you're standing near a jet engine, we're going to look up to 120 to 130 dB, and that's going to be right at the upper end where things potentially are damaging to our ears. Now, I said we want to talk about acoustics, right? And we want to talk about the environment and how sound works in the environment. And so far, I've just talked about the idea of a single sound source that's sending a wave front from the sound, traveling out into the air, and presumably it eventually reaches somebody's ear so that we can hear it. And that's called direct sound, right? The actual sound wave that goes directly from the sound source, such as my clapping hands, to your ear, and that's the direct sound. And it could be that we might be in an environment where that's the only sound that you hear. This is called a free field. But natural environments are not free fields, right? So we're also going to have, in addition to the direct sound, we could have what we might call reverberant sound or indirect sound, which is some of the sound created when I clap my hands will go straight to someone's ear, my ear in this case, but it might also hit the wall in front of me. And then that sound wave that hits the wall in front of me bounces back and echoes back and arrives at my ear a fraction of a second. See if I can do this. I don't know how well this captures from your speakers here, right? But there's a difference between the way the clap occurs and sounds in a room with walls compared to in a broadcast studio that maybe has sound absorbing material all over the walls, and it has a much drier sound that doesn't have that delayed reverberation. Or if you're just in a completely empty space where there's nothing for it to reverberate from. But that's where things start to get into a little bit of a fiction. And so it's probably fair to say that a so-called free field that contains no reverberation and sound reflection whatsoever and only contains direct sound is essentially a fiction. So if it was possible to create a sound in an environment where there were no surfaces at all, blank empty space, and there was no reflections, you could have nothing but direct sound. But of course, such environments don't exist. We can replicate them in what are called anechoic chambers. So an anechoic chamber is essentially a chamber that's designed to prevent echoes or to prevent sound reflections or reverberation. And so they have specialized panels on the wall that are designed to capture the sound so that it absorbs all of that sound and prevents it from reflecting back to any person who might be there. Now, these kinds of anechoic chambers can be either fairly cheap and simple, and they only do a decent job of absorbing sound, or you can have some that are really, really expensive and just dedicated to really maximizing the amount of absorbed sound that we do here. And these might be able to absorb something like 99.99% of the sound. There's also some stuff you can look up on YouTube of the quietest room in the world, and that's what that is. But it's not 100%, right? And so it can do a very good job, but it's not really technically a true free field. Here is a graphical depiction of what we're talking about, of that sound source that creates the sound wave, the pressure front that heads out really in a sphere, even though it's not really depicted three-dimensionally here. And that pressure wave is a direct sound source. You're going to have that one arrow that continues on to the person's ear. But as noted, the sound wave can interact with the surfaces in the environment and sometimes reflect off of the environment in a way that's very much like what we see on the left here, right? Just a fixed angular bounce of the sound wave off of a surface. This kind of direct reflected sound occurs with certain kinds of specific surfaces, right? So you might imagine that the nature of the surface will determine how that sound reflects off of it. So smooth surfaces, like especially like glass and mirrors, just like they reflect light and by fixed angles, they can also reflect sound waves in a fairly nice reflective way like that. Plywood and concrete also do very similar things. They reflect sound like this. But let's imagine a surface that doesn't have such a smooth surface on it, but it's more of a variegated surface like we see in the middle here. What would that look like? Well, that would be like putting carpet or drapes on a wall, right? And so at the microscopic level, it has lots of tiny little holes and variegations that will help absorb that sound. And whatever sound does reflect from it, some of it gets bounced around inside those little crevices, and that helps absorb the sound. But anything that does get reflected kind of gets reflected in random directions. And so the sound gets kind of scattered in all directions. And then there's also what's known as diffraction. So imagine a really powerful sound wave that hits a wall and makes the entire wall vibrate. And now the wall vibration just kind of essentially ends up sending additional sounds out in all directions from the wall itself. You've experienced this in your car. If you've been in a car and some person next to you has a big subwoofer in their car, and you feel that heavy bass that rumbles their whole car, it rumbles your car, and then you hear this low bass coming out of everything around you because that's the diffraction effect, right? Everything is vibrating now. So now that we imagine we have a situation where we have a natural environment that's going to contain reverberant sound, and there's going to be different kinds of surfaces that reflect the sound in lots of different ways. Another thing we want to keep in mind is that those different reflected sounds come from all directions and have to travel different distances to get to the person's ear. So here we see a depiction of maybe a person on a stage playing a guitar. You've got a listener in the environment that is seated for a certain distance. And so certainly the direct sound is going to be the sound that gets to our listener first, right? That is the shortest distance between 2 points is the straight line, and the direct sound travels the straight line. So it gets there first. But you're going to have all this sound bouncing off from all of the different walls and ceiling of our environment, of our room, our stadium or theater or auditorium, right? And depending on how high the ceiling is and how wide and how far back the walls are, that determines the distance all of that reverberant sound has to travel. And longer distance implies then it takes longer before the reverberation finally gets to our person. So clearly large stadiums have lots of reverberation, lots of echo, whereas a small, intimate, nightclub is going to have less reverberation, right? But it also depends on what's covering the walls. So if our big stadium just has lots of concrete floors and walls and plastic seats and so forth, then it's going to be really echoey because you're going to have lots of that reflected sound. But if our nightclub has carpeted walls and so forth, then we're going to absorb a lot of that sound, and it's going to have less reverberation. It's going to be much cleaner sound, much drier sound is usually the word we use to describe lack of reverberation. And this graph on the right kind of captures some of this, right? We have the initial sound pulse that occurs at time t0, and then at some period of time after that, the direct sound hits our listener, and then there's going to be some of this reverberation that occurs and spans out over some period of time. But it all is really quick, right? And that decay of that lingering reverberation or echo then helps capture the quality of the sound, right? And what it's going to sound like, whether it's going to be nice and tight, if there's small and lots of sound absorbing material, like an anechoic chamber, you're not going to see essentially any reverberation, very minimal. But a big empty stadium, and somebody hits a drum in a big empty stadium, you're going to see a long reverberation envelope like this, right? So one other question we can try to say here is, can we calculate the reverberation time? That is the total time it takes for all of that reverberant sound. And well, we can, right? We have formulas for this. So as I noted, it depends on the room volume, right? How big is this room and how much space is there for this sound wave to travel? And we also want to know how much the surface area is, right? So how many different surfaces are there? Because it's one thing to have an empty room, and so the sound is going to reverberate just from the walls and ceiling and floor. But if there's all kinds of other stuff in the room as well, then that other stuff increases the surface area, and sound will reflect off of that too. And so the ratio of volume to surface area is going to be an important factor here. So as we increase the volume or decrease the surface area, this increases our total reverberation time. But we also need to factor in something else, which is K. And so K is called the absorption coefficient. And so that also going to makes our calculation a little more complicated, because in a natural environment, not everything is made of the same material. So we might have to separately calculate the surface area of everything in our environment that might be made out of wood or concrete, because that's going to have a different absorption coefficient compared to everything that might be covered in some sort of carpeting or drape that helps absorb the sound a little bit, which will have a higher absorption coefficient and therefore differentially affects our reverberation time. I have some sample values over here of different absorption coefficients. So the higher it is, means the more sound that we're absorbing. So highly specialized acoustical tiles that we would use in anechoic chambers have an absorption coefficient of 0.99. Plywood is very low at 0.09. That means it pretty much reflects a lot of sound. Concrete and glass also reflect a lot of sound. But once we start putting up heavy cloth on the walls, we see that even though it's not perfect, will still absorb quite a bit of sound. So in order to accurately sort of calculate the total RT reverberation time for a given environment, this is what we have to do, right? We have to sum up all of the surface area for different surfaces of different materials, and then using that particular absorption coefficient, calculate this number and combine that with the values with the other surfaces. And so the actual calculation of RT can be a little bit of a bear, but the basic idea, the basic principle, you can see here, right? That room volume, surface area, and surface material all are relevant to determining the total reverberation time. And one thing that we might want to also then take from this is that different reverberation times are important here, because when sound is very reverberant, well, that might create a certain liveliness for maybe a musical performance that is desirable. But when we're talking about listening to, say, a speaker who is trying to obviously convey something through their vocal presentation, we want to improve speech intelligibility. And the more reverberation there is, the more the speech just becomes just like, oh, rah, 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 right? It's just, you can't really make out what the person sounds, because all you hear is echo that starts to interfere with the direct sound, and it becomes unintelligible, right? So we have some different recommended reverberation times here. So in a classroom where obviously hearing someone speak clearly is very important, we want to have reverberation times down around 0.4 to 0.6 seconds, right? But in a gymnasium where people are doing more sports kinds of things, and hearing a voice is less crucial, then we can have longer reverberation times, right? Now, when it comes to how we perceive the sound, we want to talk about perceiving the qualities of the sound. And one way to talk about the qualities of the sound is to talk about the pitch as well as the loudness of the sound. And so pitch and loudness are differentially described here because we might think that, well, going back to the physics of sound, maybe the different frequencies that we talk about, if you go to those different YouTube channels that I talk about and listen to a 5,000 hertz or a 600 hertz, 500 hertz or 600 hertz or 1,000 hertz tone, you're going to clearly notice that the difference between them are just purely their pitch, right? As you increase the frequency, it increases the pitch, and that's very obvious. And likewise, that the decibel level corresponds to the pressure level or amplitude, and therefore the perception of loudness. High dB means a much louder sound, clearly. But unfortunately for us, if we want to think about it, try to predict the exact result, that if I know the exact dB level, can I predict exactly how loud this is going to sound to a person? The answer is less clear cut. And so what I said before, we have to keep in mind here that our hearing is most sensitive around a range around 1,000 to 4,000 or 5,000 hertz. And that means that the loudness of the sound is not strictly a function of the decibel level, because when we're dealing with sounds that are in that range, then it's easier for our ears to detect that, and therefore those sounds can actually be perceived as louder than equivalent decibel level of sounds that are outside of that range. So as an example, if I played to you a tone at 4,000 hertz and it has a certain decibel level, like let's say 50 decibels, that's going to sound pretty loud to you. But if I take the same another tone that's maybe 200 hertz, and I also play it at 500 decibels, so it's got the same decibel level, 50 decibel, I got my numbers mixed up, sorry. Even though it's the same amplitude, the same decibel level, the 200 hertz tone will not be nearly as loud as the 5,000 hertz tone. And that's merely because of the fact that even though the only thing that we've changed is the frequency, and we would think that should only change the pitch, it also changes your perception of its loudness as well, because our ears simply just do not detect those 200 hertz tones nearly as well as they detect the 5,000 hertz tone. And this graph shows us that more or less clearly, I should hope. So what we're seeing here is that there is this dip right there. So right around 1,000 hertz in the middle, right? We see that that's where our hearing gets very, very sensitive, but it continues to improve in that upwards towards the 4,000 to 5,000 hertz range there, right? So what I said before is true here. Hopefully you can see my mouse pointer on the screen here, that if we were to take a tone that is presented right here where the mouse is, and that would be reported as having maybe a decibel level that we can't see the whole of the y-axis here, but that would be like essentially maybe 2 decibels essentially, right? So we don't have to present much more than a very, very weak stimulus in order for a person to say that, yeah, that sounds, I can hear that, right? And if I were to then present another tone, let's go to 100 hertz on the x-axis here, and I present that at close to 30 decibels, a person will report that that has the same perceived loudness as our 2 decibel tone at 5,000 hertz over here, right? And so all of the points on this heavy line marked with a 10 and are perceived as being equally loud. And so we're going to use a subjective loudness scale called the phone scale, right? And so everything on this curve is reported as being 10 phones, which means a certain subjective amount of loudness. So note there that the decibel scale doesn't specifically correspond to perceived loudness. The decibel scale is really a measure of the pressure level, right? The logarithm of the pressure level. The loudness can be measured on more of a subjective scale called phones. And on all of these are called equal loudness contours, because everything on one of those curvy lines is perceived as being equally loud, despite the fact that they might have drastically different decibel levels. But that's because of the interaction between the frequency of a tone and the decibel level or amplitude of the tone together determines our perception of its loudness, right? So that's just another fact to keep in mind here, that how loud a sound is is not strictly a function of its decibel level. It's also a function of its frequency. We have to account for those frequencies that people are more sensitive to. There's another thing we need to talk about when it comes to acoustics, which is how do I know where the sound is coming from? And that could be useful for a variety of situations. If I need to respond to a sound because something bad's happening over here in my environment, if I'm working in a factory and there's a piece of machinery that's malfunctioning and a warning light buzzer, is coming off of that machine. Obviously, a light would help too, right? So you can look at that light and know which machine is malfunctioning. But if it's just a warning buzzer that you're hearing, you might want to be able to localize that sound to know where it's coming from, right? And we can do that. We can tell the direction of a sound source. We can even potentially tell the distance of a sound source. That's a little trickier, but maybe one thing we can do, not necessarily is accurately detect the exact distance of a sound source, though in many cases we can. But we can also detect a change in the distance. So is the sound approaching me, right? We all know this. We can, if you hear a car, if you're standing on the sidewalk and your car is coming, you can usually detect that the car is approaching because the sound's getting a little louder, right? And then when it passes you and it starts to get a little quieter, right? And so this change in the intensity of the sound is specifying approach and retreat like that. Now, if you've ever been to a race, like a car race like the Daytona 500, you'll also notice that as those race cars approach you, not only do they get louder, but you get a pitch shift as well. And this is called the Doppler effect. And so this effect that creates that ring, that sound, that kind of increasing pitch like that is also a function of the change in distance, right? And so again, distance affects not just loudness, but it even can affect pitch there. If there's a sufficiently rapid change in distance anyway, right, will create a noticeable change in the pitch of the sound coming from that object, whatever it is, a race car, whatever it might be. So we want to know a few facts about how people localize sounds. And one thing that we want to note here is that complex sounds are more easily localized than pure tones. So a very simple, obvious implication of this is that if you have a warning tone and you want to, like I said before, you've done a spectral analysis of the noise of an environment and you determine that maybe a 12,000 hertz tone is the appropriate warning tone for this environment because all of the noise falls pretty far away from 12,000 hertz. And so you say, well, I can use a 12,000 hertz tone because that makes it sufficiently distinct from all of the frequencies of the noise in this environment. But if you do this as a pure tone at 12,000 hertz, even though it might be easy to hear and detect that presence of that tone, a person might not be able to localize the tone. And if that's important, if you need to include the fact that a person needs to not only hear the warning siren, but also be able to tell where that warning siren is, then using a pure tone is not going to be a good idea here. You're going to want to use complex tones. You're going to want to have many frequencies layered together to create more of a, instead of just a dee kind of a sound, you're going to have something maybe sounds like a buzzer, right? That because that has more frequencies, right? Let's talk about how we localize sounds. First is the arrival time difference between the two ears. And so here we're going to say that if a sound is to your right, then it makes sense that it's going to arrive at your right ear a fraction of a second, right? Sound travels at a specific speed, 700 some miles per hour, right? So it's going to arrive at the right ear a fraction of a second. And it is only a fraction of a second. You see the numbers here, right? When the sound is nearly fully off to the side, 80 degrees away from straight ahead, 90 degrees would be fully off to fully exactly to your right. The arrival time difference between the ears is 0.71 seconds. But when it's just slightly offset, just a 10 degrees off from straight ahead, right? It's a very slight change there. We see the arrival time difference is pretty small. It's 0.089 seconds. But we can hear that, right? So we can hear even down to 30 microseconds in terms of arrival time differences. So we can detect little small deviations in position like that because they create small differences in the arrival time. there's actually a comparison center in the midbrain. So when the signals come from the two ears arrive at the midbrain to get integrated and then sent to the higher parts of the brain, there's a comparator in the midbrain that's detecting the arrival time differences down to these millisecond levels, right? And it's using that to help localize the sound source. Of course, this also means that if arrival time between the two ears is important, then anytime the sound arrives equally at the two ears, we would expect it to be perhaps not off to the side, but straight in front of us, except there's some ambiguity, because if the sound is above us or behind us, it will also arrive at the two ears simultaneously. So we're going to call this a zone of confusion, where we would not necessarily know whether that sound is truly right in front of us or behind us, because of the possibility that either one could result in the same arrival time. And the same is true, by the way, of not just the straight ahead and straight behind, but what if it's 10 degrees off to the right, it could be 10 degrees off to the right in front of us, and we would have that 0.089 arrival time difference. But it might also be behind us in 0.89 or 10 degrees off to the right, in which case, again, that would be another zone of confusion. So we might think that there could be some issues that we might be confused sometimes about where sounds come from. And well, there's two things to say about that. One is that this occurs, right? That sometimes people are confused about where the sound comes from. But number two, one thing that we can do is simply just move our head, right? So if the sound is directly in front of me, but I think it might be behind me, and I'm not entirely sure, if I just tilt my head a little bit like this, then that's going to immediately resolve that sound confusion, right? Because now by turning my head, it's no longer directly in front of me. Now it's a little bit closer to, if it was really in front of me, I've just now put my left ear closer to the sound source, and my right ear will be pointing behind, right? And that will help resolve the ambiguity. And that same thing would occur in any zone of confusion. Just small head turns will help resolve that. In fact, one thing you'll notice is that a lot of animals, rabbits being an excellent example, they move their ears a lot, right? So, if they might perk up and raise their ears up when you get startled them, but you'll see, you can't see me here, right? They might do these things where they're pointing their ears in different directions because they're really trying to resolve. They do a lot better job localizing sounds than they maybe even do with vision, right? Their hearing is much better than that. So that's what they're trying to do, is really map things out. Where's the threat? And they can localize pretty well with their ears. So there's other information that we can use though. So not only does the sound arrive at one ear first, right? If it's to your right, it arrives at the right ear before the left ear. That's the arrival time difference. But it's also going to be louder in the right ear compared to the left ear. And this is an effect known as a sound shadow. And so together with the arrival time, the intensity difference between the two ears is going to help kind of provide redundant information here about the loudness, right? Now, the direction. The distance is also relevant here. So I was mentioning that we might be able to localize the distance, and that the idea is that as a sound source gets further and further away, then what has to happen is the sound wave has to travel a further distance. And this sound wave is just going to simply lose energy. And there's a physical law that describes how these waves lose energy as they travel some distance. And that's the inverse square law, right? So the idea is that we're going to lose sound pressure. SPL is the sound pressure level. So we're just going to lose pressure as a function of the square distance that we have to travel here, right? And so certainly, far away sound sources are going to be quieter than up close sound sources because of the inverse square law. Now, whether we're able to accurately localize distances, if I just hear a voice, do I know that person is 2 feet away from me versus 20 feet away from me? Well, in general, yeah, I might be able to know that when a person is really close to me when they're speaking versus when they're far away. But could I close my eyes and judge precisely the exact distance of that person? And the answer is maybe not. But certainly I would know relative terms, close versus far. And like I said before, if the person is moving, I know if they're approaching or getting further away, right? Now let's talk also about, so that's here's a graph of the sound of the inverse square law, but also it's worth pointing out that it's not necessarily completely universal. The decay of the sound pressure level will be partly a function of the frequency. So different frequencies, higher frequencies drop off even a little more severely as a function of distance. So only lower frequencies travel well. Now, when it comes to the sound shadow effect, the idea is that this only works for specific frequencies as well. So it works best for high frequencies. So what we're seeing here is not necessarily, I was talking before about a sound shadow essentially created by the head, so that when a sound is coming from your right, it's louder in your right ear. But as it passes across your head is casting a shadow for the sound. So just like an object will cast a shadow for light, it casts a shadow for sound. And so it's a little bit quieter on the left side of your head because of this sound shadow. But here we're depicting it not with a person's head, but just with an obstacle in space. And so this is also true, though, in a natural environment. If you are on one side of a building, let's say this obstacle in the middle, this big rectangular block is a building, and you're on one side and there's something making sound on the other side, then certainly there's going to be a shadow zone, right? If you're standing on the back side of the building relative to the sound source, it won't be so loud, right? But it does depend on the frequencies of the sound. So what you're seeing here is that when the frequencies are high frequencies, and that means the spacing between the peaks and the sound wave are smaller than the width of the building, then you get a very pronounced shadow zone. But when you have a lower frequency, so that the spacing between the waves are much larger than the width of our building, now what's happening is that the waves essentially envelop the building and swallow it up, and there's much of a reduced shadow. So now that applies for localizing sound with our heads, because when the sound waves are high frequency to the point that they're smaller than the width of your head, then you're going to have a nice strong shadow zone, right? But when they are longer frequencies, lower frequencies, and the waves are more spaced out, then those waveforms will envelop the head and essentially not have a noticeable change in loudness. So you're going to have more of a noticeable localization here, at least using the intensity difference only for high frequency tones. So when talking about the practical uses of this information, we could say here that when we're designing an auditory alarm, that is, we're going to make buzzers and warning sirens and things in our environment, we want to make sure that it is a good rule of thumb is 30 decibels louder than the background noise, right? Of course, that also means, though, that we have to be mindful of the fact that we don't want to damage the hearing of our people that are going to be hearing these. So even though we want to have it sufficiently loud to be detectable, we also don't want to go into those 120 dB ranges where we're going to hurt somebody's hearing. So we're going to try to limit it to about 90 dB, and that's going to keep it reasonably safe. And as I noted before, we want to make sure that the pitch of our warning tones must be distinguishable from the noise. So if we do that spectral analysis of the noise, we will know what that is. It's also important to keep in mind here that there are many environments where we might need to deal with multiple alarms. A typical example of this is a hospital or medical setting. So nurses, for example, might have to deal with all kinds of different alarms that are going off all the time. And in those situations, we need to make sure that we can sufficiently distinguish the different alarms from each other. And that means maybe using different pitches, but we also have to be concerned about the fact that a human's ability to distinguish different pitches is not necessarily very good. Some people might have perfect pitch and therefore can easily distinguish small differences in pitch. And they also have a good relative pitch where they can distinguish those small differences. But not everyone does. And so we have to account for the fact that some people are just very poor at this. And so if you're going to distinguish warning tones by their frequency or pitch, you want to make sure that the difference is really large, like a really drastic difference in pitch. But what you can rather do is manipulate what's called the timbre of the sound, right? And that means that's usually what we call the quality of a tone. So that's the difference between things like, again, beeping sounds, beep, 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 versus those annoying buzzers that go, right? And so those are different timbres, right, that have different qualities and different convey different, you can even convey different things. Sometimes repetitive beeping sounds more like a nice pleasant thing. Sometimes you get those buzzers that have more of a clear, obvious negative implication behind them. And you can also vary the timing, right? You can do slow beeps and fast beeps and things like this, and different patterns, different sound patterns like this as well. And of course, always keep in mind the equal loudness contours, as I mentioned before, that people are going to have certain sensitivities. And so if your warning siren has to be in a range that people are not sensitive to, you might need to bump up the decibel level a little bit. All right, well, that wraps up our hearing content. So next time we'll be talking about touch and haptics.